Next, we jump on the chapter 8. Chapter 8 called Viscous Flow in Pipes. So in this chapter, I'm working on problems 8.3. The problem is like rainwater runoff from a parking lot flows through a 3 feet diameter pipe, completely filling it. Whether flow in a pipe is laminar or turbulent depends on the value of the Reynolds number. Would you expect the flow to be laminar or turbulent? Support your answer with appropriate calculations. So we know that Reynolds number, the flow is turbulent when the Reynolds number is more than 4,000. So we know earlier that this is the equation of the Reynolds number, the calculations formula, the density times velocity times diameter per viscosity, or the velocity times diameter per kinematic viscosity. So to calculate the speed of the flow, we are assuming that this is a laminar flow. So we can assume that the Reynolds number equals to 4,000 and not more than 4,000. Moving on from that, we can calculate the velocity, Reynolds number times kinematic viscosity per the diameter of the pipe. So 4,000 times 1.21 times 10 to the power of minus 3 feet, feet, feet squared per second per 3 feet equals to 0.0161 feet per second. So if the speed of the flow is more than 0.0161 feet per second, it is possibly that the flow that the kind of the flow is possibly turbulent and not laminar. That is the solutions of the problems 8.3. Next, we jump on the problems 8.8. The problem is carbon dioxide at 20 degrees Celsius temperature and a pressure of 550 kilopascal, and it is an absolute pressure, flows in a pipe at a rate of 0.04 Newton per second. Determine the maximum diameter allowed if the flow is to be turbulent. So we can start to solve this problem by knowing in the first that Reynolds number is the flow is turbulent when Reynolds number is more than 4,000. Where we can start from the formula of Reynolds number is that 4p times K per p times kinematic viscosity times diameter equals to 4,000. Thus, diameter equals to 4 times p times K per 4,000 times p times kinematic viscosity, where the G times p times K equals to 0.04 Newton per second that we know from the problem. And also we know that the kinematic viscosity is 1.4 times 10 to the power of minus 5 Newton second per meter squared. We can get this number from table 1.8 in the Monson book. So lastly, we get the diameter. We input the number 4 times p times 4 times p times K. Then we convert it to meter per 4,000 times p times 1.47 times 10 to the power of minus 5 Newton second per meter squared. We get the final result as 0.0883 meter. So yeah, that is the maximum diameter allowed if the flow is to be turbulent for the pipe. Next, we move on to chapter 9, flow over immersed bodies. In this chapter, I will explain the solution of the problem 9.43. The case is a baseball is thrown by a pitcher at 95 mile per hour, through standard air. The diameter of the baseball is 2.82 inch. Estimate the drag force on the baseball. So, uh, from we know from this chapter that the drag force can be calculated by using drag coefficient, or CD, times a half of density of the fluid, times velocity squared times A. So at velocity we can convert it to from mile per hour to feet per second, and then we can calculate the Reynolds number. Then we get the Reynolds number is 2.09 times 10 to the power of 5. From we are assuming the drag coefficient of the baseball is 0.5. So moving on that, we can calculate the drag force using 0.5 times 1 out of 2, 1 per 2, times 0.00238 slugs per feet cubic. This is the density of air in slugs per feet cubic, times 139.3 feet per second square, and then a quarter of P times 2.82 per 12 squared. Then we get the drag force is 0.5 pound. So that is on how to calculate the drag force of the baseball thrown by a pitcher. Next, we jump to the last chapter of our study in fluid mechanics. On chapter 11, we are learning about compressible flow. On this chapter, I will talk about the problems number 11.19. The problem is determine the Mach number of a car moving in standard air at a speed of A 25 mile per hour, B 55 mile per hour, and C 100 mile per hour. So we know the definition of Mach number is a ratio of a local velocity to a speed of sound. So that the formula of Mach is V per C. For standard air, we can calculate the speed of sound in the standard air, that it is a root of R times the temperature times the K. We can calculate, we get the velocity of sound on standard air is 1117 feet per second, or in mile per hour it's 761.6 mile per hour. So moving on that, we can calculate the on car moving in 25 mile per hour. The Mach is 25 per 761.6. We get the Mach number is 0.0328. For car moving in velocity 55 mile per hour, the Mach number is 0.0722. For car moving in 100 mile per hour, we can calculate the Mach number is 0.131. Mach number. So that's it for the compressible flow chapter, and I think that's a wrap for the learning from the problem exercise of fluid mechanics based on Munson books. So if you have any questions or any advice, any critics, please don't be hesitated to comment on my post in Society Online, so that I can answer your questions and make your transfer my knowledge to you directly. So thank you for your attention. Yeah, see you later. Assalamualaikum warahmatullahi wabarakatuh.